Now we want to look at the parts of Gibbs free energy and see how they affect why something is spontaneous. So if we only want to know, is a reaction spontaneous, we only need to figure out the sign of delta G. Positive delta G is not spontaneous reaction. Negative delta G is spontaneous. So the reason why we define and look at the enthalpy and entropy change is that these components, what make up the delta G, can tell us why a reaction is or is not spontaneous under our given conditions. So these two factors, we can kind of understand how they inform or kind of describe spontaneity. And so for enthalpy changes, negative enthalpy changes are favored. Negative enthalpy in processes with negative enthalpies are exothermic, so you're releasing energy. In the context of a chemical reaction, that means your products have more stable chemical bonds. So really, enthalpy is really looking at chemical bonds and how strong the chemical bonds are. And in an exothermic reaction, your product has stronger chemical bonds, and in an endothermic reaction, the reactants have stronger chemical bonds. So you're breaking those chemical bonds. And so for a process that's exothermic, that favors spontaneity, but we know that's not the whole story because entropy also affects it. So for an entropy, a process where the entropy is greater than 0, that would also favor spontaneity. That lines up with the second law that things tend to go to disorder. Those molecules are moving randomly. They're going to change in such a way that leads to most randomness, or that follows from that random motion. The most likely outcome is the disordered outcome. And so every process has an enthalpy and an entropy change. And those don't necessarily go in the same direction in terms of favoring spontaneity, but their combination is what determines the delta G, and that determines the actual reaction spontaneity. So you can't tell spontaneity from just delta H or just delta S. You need to account for both of them. So since there are these two factors, delta H and delta S for a reaction, we know that we can basically classify, they're both either going to be positive or negative, and those both kind of inform whether or not the reaction is spontaneous or that favors spontaneity. And so, I've color coded here. So the exothermic tends to be spontaneous and positive entropy tends to be spontaneous, whereas endothermic and decrease in disorder for the reaction tend to not be spontaneous. So if it's an exothermic reaction and delta S is positive, then both of those are good things. Those are always spontaneous reactions. So these are reactions like combustion of propane. These are the kinds of reactions that we use to power stuff. Battery reactions happen in this way. And so there's a lot of always spontaneous, a really strong drive to have this process occur. Really always spontaneous because chemical bonds, you have more stable chemical bonds and more disorder. So everything's pointing in the same direction. Conversely, if you have an endothermic process that would decrease the disorder of the system, that would be never spontaneous. Both the entropy side of the reaction is unfavored and the enthalpy side. So it's more ordered and less stable chemical bonds. That's just not, those processes just aren't going to happen under your given conditions. So then we have these kind of mixed bag where, for example, you have a process that's exothermic, but it also decreases disorder. Okay, so exothermic, you would say that is what would be favored, right? That you're forming more stable chemical bonds, but you're decreasing the disorder of the system. And so one of those is going to win. And so in order for this process to be spontaneous, it has to be the enthalpy that wins. And we call that an enthalpy-driven process. The change in entropy of the process is not favored for spontaneity. Okay, so this is only the enthalpy change. The forming more stable chemical bonds is what makes that reaction occur, if it will occur. Those processes are only spontaneous at low temperatures, and that's a relative term that we'll explore more. On the other hand, if delta S is positive, but if delta S and delta H are both positive, that would be an entropy-driven process. So that would be where delta H is positive, so it's endothermic, so that does not favor spontaneity. So the reason why it's spontaneous is because of the entropy factors. That increase in disorder is what would drive this reaction to happen. These are spontaneous at high temperatures. So this enthalpy entropy driven comes up when delta H and delta S have the same sign. This is entropy driven is when they are both positive. If I can draw a positive side, enthalpy driven is when they're both negative. That's supposed to be a negative sign, sorry. So let's look at some examples of these. So the reaction we looked at before, barium oxide plus carbon dioxide becomes barium carbonate. They're both negative, exothermic and decrease in entropy. And we can understand what those mean. Negative enthalpy means it's exothermic. That means we form strong bonds. Barium carbonate has crazy strong bonds. There are very, very strong bonds in here. This is a very, kind of stable chemical from that position of just the strength of the bonds. But in order to gain those strong bonds, you have to kill a gas molecule. And so that would be a major, major loss of entropy. But we just calculated that this is spontaneous at 298 K. Because the benefits of forming these chemical bonds, these strong chemical bonds, outweighs the cost of losing this gas. So when we say that the reaction is enthalpy driven, we can understand that the change in enthalpy, those formation of strong chemical bonds, is what makes this reaction actually be spontaneous, not the entropy change. The entropy change is not favored here. And we said enthalpy things were at low temperatures, so that's a relative term. Here, 298 K isn't exactly cold, that's room temperature, right? But it is low in the scheme of things, in the scheme of this reaction. There we'll see where that temperature kind of cutoff is. So we can look at another example, say from when we were looking at the second law, where boiling water, going from liquid to gas phase water at 298 K. Delta S for the reaction was positive because you gain gas. So from an entropy perspective, this reaction or this process is favored, but from an enthalpy perspective, it's not, because you are having to break hydrogen bonds. That is not favored. Okay, and so that's why we say this is an entropy-driven process. We could also predict it just from seeing that both of them are positive. Right, we have positive enthalpy and positive entropy changes. At 298 K, while this process is entropy driven, at 298 K, the entropy push is not enough. So we know that it should be, that if this process is going to be spontaneous, the entropy change is going to be what's driving it. But that doesn't, basically, it's not enough here. It's not enough to overcome the cost of breaking those hydrogen bonds, the kind of the enthalpy cost of breaking those hydrogen bonds. But entropy-driven processes, if you become spontaneous, we said at high temperatures, and we already have kind of discussed that would be what you could do to get water to boil, is increase its temperature. All right, so let's get some practice at identifying whether or not a process is entropy driven or enthalpy driven. I have two reactions here. It's 4pH3 gas becomes P4 gas and 6H2 gas, and then the delta H is 373 kilojoules per mole. And the second process is freezing a liquid into a solid. So let's take a look at these.
All right, so I want to know if each of these is either entropy driven or enthalpy driven. And if we want to know that, really what we're looking for are the signs for delta H and delta S. We are basically implying when you use one of these terms, you're implying that there's kind of a conflict between the change in enthalpy and the change in entropy in terms of determining spontaneity. One of them is a change that leads to something, process wanting to happen, and the other one's kind of pulling it back. So we're going to see which one is favored. And so my first reaction, I have 4pH3 becoming P4 and 6H2. And the delta H is given to us. So delta H is 373. So I know right away that delta H is positive. So then I want to look at my delta S terms. And so in that case, I'll have to predict what the sign is. We could look up reference information and kind of figure out, what is the entropy for all these things. Or all we really care about is the sign. So we can just say it's 4 gas, becoming 1 plus 6 is 7 gas. That's an increase in gas, right? 4 to 7 is an increase. So because of that, we would expect that delta S also be greater than 0. Both of them are positive. So once we know they're both positive, we could just kind of remember that that means entropy driven. And basically the reason is because delta H positive, that's endothermic. That means you are breaking stable chemical bonds to form less stable chemical bonds. So that's not something that wants to happen. So from the enthalpy perspective, this is not a good chemical reaction. You're putting in energy to form less stable chemical bonds. But you get some nice disorder. And so that's going to be our question, kind of what is kind of the preferred factor there. If this process were to happen, it would be because of the change in entropy. That's what entropy driven means. That if this process is going to occur, it has to be because of that increase in disorder. It's not because of the chemical bonds making strong chemical bonds or releasing energy. It's all about the entropy side of things, and that's why we call it entropy driven. If we look at freezing a liquid into a solid, so we don't know what we're looking at here. This is actually just generally true for freezing any liquid into any solid, but we know we can predict things about this. So freezing a liquid into a solid, freezing is always an exothermic process. So we know that delta H is going to be less than 0. And that's always due for freezing because you form better intermolecular forces. Right, that's why it's exothermic to freeze. And then you also have from liquid to solid, that would be you're taking motion and removing it, going to solid. So delta S would also be less than 0. So you are forming nice intermolecular forces. The molecules stop moving so they can perfectly line up. You get some nice hydrogen bonds, dipole-dipole, even dispersion, right? There's stronger intermolecular forces whenever you freeze. So freezing is always exothermic because you're making these nice strong interactions. But in order to make those strong interactions, the molecules have to stop moving. And that is not favorable. And so because they're both negative, this is enthalpy driven. And these ideas a lot of chemical processes, you tend to have this kind of conflict where, you want to make good, strong chemical bonds, but you got to sacrifice disorder to do that because strong chemical bonds are all about kind of locking atoms into place, not having gases anymore, not having disorder. But if you break some chemical bonds, like up here, you can get a lot of disorder. So a lot of chemical reactions, you have this idea of entropy enthalpy compensation, where basically they're working in opposite directions. And that actually helps us because we're going to see that's going to allow us to control when and how chemical reactions become spontaneous.
Okay, participation 1031, no questions in this one. We are halfway through the set of videos. Maybe some questions in the back half. See you there.